Hey guys, so previously we derived the weak form, and now I want to kind of wrap up the properties of this bilinear form here, which essentially is a statement about the internal energy change whenever we probe this region with some test function. And one of the properties here is symmetry. So if we switch, u and v as our inputs, they should be equivalent to each other, okay? And this has a physical meaning because we can have the symmetry if and only if reciprocal work. Reciprocal. Sorry, my brain just farted. But reciprocal work, which you can kind of think of this as like Hooke's law, but a little more generalized. I think it's called Betty's theorem in elasticity, but that's essentially what's happening here. Okay? So, however we tug on it, we should have this reciprocal virtual work that is done on this region. The next thing is the idea of coercivity. So if I were to take the the energy bilinear form of itself with the test function of itself, this should be the upper bound on the gradient, on the norm of the gradient in Hilbert space of the test function, and this should be bounded below by some alpha, where alpha's alpha's greater than 0, by the norm of the function itself in a Sobolev space. All right. And again, this property is called coercivity, and this is another physical meaning, which is we have this if and only if there's positive stored energy. Okay. And another thing to note is that rigid motions of this region cost 0 energy, and the rigid motion would cost 0 energy only if it's forbidden by the boundary conditions, all right? And so that's why positive stored energy, if we have positive stored energy, then we know that it's coercive. The last thing is continuity. So if we have, the size of this energy bilinear, this should be bounded above by the norm of the actual field multiplied by the norm of the test function in the Sobolev space, okay? And this M, again, is kind of like a delta epsilon type of bound. And this is, if and only if we have bounded energy exchange. Okay? And using all three of these, 1, 2, and 3, using all three of these really physical statements about the region, given our particular weak form, okay? If we obey these three constrictions, you can then use this in the proof of the Lax-Milgrom theorem. And the Lax-Milgrom theorem guarantees that there exists a unique weak solution in the vector space, or in the Sobolev space, and this is a mathematical translation of, you can think of this as, a stable equilibrium exists and is unique. So we're relaxing our assumptions. The heat source is not going to be actually a specific point in a sense that blows up, where the gradient blows up to infinity, because it would take an infinite amount of energy to have that. So what we need to do is first of all say it needs to be symmetric, right? It needs to be coercive, and it also needs to be continuous. And so this weak form is actually a lot more physical in the sense of a problem that we can actually really solve without any infinities blowing up. Okay. Now, what we need to talk about is preparing this problem to be solved with a computer. And so what we're going to do is take this same kind of, domain a little bit, but instead, what we're going to try to do is we're going to try to partition it into finite elements. All right? And let's put some dots here on the domain. So first of all, what we're going to do is each of these nodes we'll call, like x sub 1, x sub 2, to x sub n, okay? And what we can actually do is really connect all of these nodes together and kind of like, do a triangulation, if you will, of everything and partition the domain in a particular way that is very interesting. So that's kind of we are partitioning the domain into just a bunch of simplices. And what's interesting about this is, again, here's our original domain. We can approximate the domain roughly. I'm not being super rigorous, but just to get the general idea, we can approximate the domain into really this, omega sub h, okay, which is equivalent to the union over all of the elements, so just the number of elements that we're using, and let's just index by e, I guess, where k of e would just represent a particular element. If we were to take the union of all the elements, we would get the full domain. Okay, and again, we were trying to make this a nice problem for a computer, so let's invent something else, which is called the tent function. All right, and all the tent function is we're going to try to make a basis that supports just the idea of bits. So I don't know. Let's choose this guy here. Let's choose this guy, and what's going to happen is we can describe a particular node at a particular node, and let's say this is some x sub I. We can describe a function that's going to go to 1 at the node and 0 everywhere else. Okay, and that's the tent function. So it's called a linear Lagrange basis function, and what this looks like is if you have some phi sub I at the particular node we're trying to describe, this would be equal to 1. But if we have phi sub j at that same node, or let's think about it this way. While this is a true statement, let's think about it this way. Using the same eigen function, if we were to do any other, it would go to 0. Okay, for all j is not equal to I. Okay. So what's happening here is we can essentially make a circuit or something like that. But first we have to talk about support. So there's something called in topology, it's called overlapping support. So the compact support is given, we can denote this by SUPP of the compact support of this with this eigenfunction. We can define this really as just the set of all x within this discretized domain with finite elements, given that well, really just for any nodes at all, the basis function for any node should not be equal to 0. Okay. So this is the support. And what we can do is wire a circuit. We can create a circuit wiring. So let's say we want to wire a circuit from over here, right? Let me use a different color here. So if we want to wire a circuit, this circuit wiring would be connected to node. So let's say node I is connected to node J. If the support of the basis function at that node I intersects the support, the compact support of the basis function J, and if that basis function is not equal to the null set. Okay, sorry about this but I can't really do nothing about that. So again, you could think about this as, let's say we have some x sub I and some x sub j, and again we are given this and we're given, this particular overlapping region where we have an intersection between x sub I and x sub j, even though these eigenbases are there. And again, let's review everything that we've done so far. So again, we have the laws of physics in energy form, but what we need to do is deal with the fact that a computer has finite memory and it cannot store a continuous function. So again, what we did was pixelate the reality here, and we chopped the domain into a mesh, and on this mesh we define really these little atoms or things that are compatible with bits, and the basis functions. We created something called a tent function, and it's really the simplest shape possible because it's 0 at whatever home node that we are. It's going to be 0 at whatever home node. 1 at its home node and 0 everywhere else. And again, this compact support idea means that what happens at node I will only affect its immediate neighbors. Okay. Because it's going to vanish everywhere else. So the solution, the solution that we are, and again, this intersection tells us that they only affect each other, and this will also lead to an idea of sparsity in graph theory. But I'm not going to get ahead of myself. What we need to do is make an assumption, a bold assumption, if you will, which is the idea that there should exist some solution U, right, to our original physics problem. That some solution U of x that should just be equal to the sum of U of j times some 5j. And for some j is equal to 1 to n. And why can we assume that? The reason why is because, well, really, we're just guessing this. There should be a way to solve this based off of the discretized way, the discrete way that we have chopped up the domain. And our goal really now, it's no longer to find some function, the goal is no longer to find some function U of x, right? That'll just be a smooth function that we're used to getting when we solve physics equations classically. But instead, we're just looking, the unknown here are these coefficients. And the unknown really dictates the height of the tent. So of course, this is our basis, right? And however we're choosing to scale it, those eigenvalues are what we're trying to find. All right? And so we're going to take our weak form. So again, our weak form, but what we can do here is take the gradient of this function here. To be equal and summing over the finite mesh that we've created, or a finite element space that is approximately covering the whole original continuous space. And what this allows us to do is get a fully discrete linear system, because we can just factor out these into columns. And this implies really just some linear equation. So hopefully you can see how the Galerkin method really allows us to do such a thing. Now I'm getting a little bit ahead of myself, but why we can do this is because, this is like kind of not very elegant notation at all, especially since we have things with linear properties. We can make the notation much more easier. But if we say, let's say we have some VH, right? And this is some vector space that is spanned, because again, remember we had the Lax-Milgram theorem here that says there exists a unique solution U in V. So if we have some V of H, right? That is spanned by the set of, let's just say phi sub 1, wherever we're choosing to start counting, phi sub 1, phi sub 2, this could be like phi sub 1, phi sub 2, and then over all the n nodes, okay? So we have a basis for every single node. If we were to find the set of all of these, they would span the finite basis space, which is a finite subspace of the infinite dimensional space that we're originally trying to solve, which is the Sobolev space with Dirichlet conditions. All right? So that's how we would rigorously try to show this. And then the ansatz, again, would be this Galerkin solution. So these, again, are scalar coefficients, or the unknowns, and these shape functions, these have known geometry or known topology. All right? They have known topology and really geometry. All right? Now, again, what we need to do is for this to work, right? For this guess to work, we need to demand mathematically that the weak form holds for all test functions in subspace. So for all the test functions that are within the subspace, this finite subspace of the original infinite dimensional vector space, we have that if we were to substitute in our finite element solution with the finite element test functions, this should be equal again to our linear functional as well. And this should be satisfied for all of the test functions in whatever finite vector that is spanned by all of those bases. Okay, and since again, since we know, so let's say since this bilinear form is linear, we can test against each tent, if you will, phi sub I. And this is why it was very important to understand previously what the idea of virtual work is, because we're going to use this same principle just computationally, okay? And with tents. So again, if you were to substitute in the, sum over the columns here, with our test function, and then here's the original Galerkin solution that we were guessing, fundamentally. That should just be a spectral expansion of the bases with different heights that are scaling the domain. This becomes completely doable, again, because we can factor out v of j and summing over all of the nodes, again, and then multiplying it by the eigenbases for at each of those points. There you go. So as you can see, that's the crucial logical step. And again, what we have now is, and instead of doing a plus, au plus b, let's call it k, because that's typically what we refer to as the stiffness matrix. But ku is equal to f. That's really what's happening here. And what k, and really, again, the unknown that we're trying to find are the finite heights of each of those basis tents. K is, let's move this over here. K is something we call the stiffness matrix in elasticity. But it has this property, right, that it doesn't go to 0. And again, remember, by the way, sorry, just a side note. The stiffness matrix is literally just the energy bilinear form for the between two nodes. Okay? That is, again, equal to the integral over the whole volume. I guess it would be finite element volume, but okay. Dx. Okay, that's what k is here. Okay, but let's make this a different color. Now k, again, it's the stiffness matrix, and it's not equal to 0. Only if nodes I and j share an edge. And that's exactly the definition of a sparse graph. Okay? Or it's very similar to how you would rigorously define sparsity in graph theory. But again, this coupling, if you will, that's what's physically happening, is, it's cataloging the energy coupling between every single pair of nodes. That's what the stiffness matrix is doing. And it's not 0 only if, they share an edge. Okay? That's really cool. That's a cool intersection. And you'll see why, graph theory becomes really, 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 really important for computers. But again, and you can think of this, physically as whatever force is on node I, on some I node, let's just say this is I node I. Whatever force is on node I, this pulling node J, that's what's happening, right? That's what the sparsity matrix is encoding. And the load vector here, which we'll call F, so this is the sparsity, or the stiffness matrix. So you have stiff, the body is, the rigid, the physical body is in its domain. Well, again, and one more thing. The tents are overlapping with each other, and this is where the circuit is really computing. Because the tents only overlap with their neighbors, this matrix, again, is going to be mostly zeros. So that's another thing to keep in mind. The F here is just going to be, again, the external force that's lumped onto each node, okay? So, F sub I, it's going to be like more of a matrix, but again, it's just the force that's lumped onto each of the nodes. So if we were to take the force or whatever determined F that we have with our original tent function and integrate it over the domain. Again, what does this mean? It's the total external force lumped onto node I. All right. And that's pretty much all I have. We, again, started with infinite calculus, this original Laplacian. And what we did after a series of just giving some physical constraints, getting the Lax-Milgram theorem, knowing that there exists a unique solution in that vector space if we have those properties. And then using those properties and creating an finite element mesh, and then kind of guessing that there might be a spectral expansion of the solution in terms of this kind of graph that we have created with some known compact support topology, and this allows you to demand a weak form that holds for all test functions in the subspace, and we then have we essentially turned this this strong form that was really not really that physically meaningful or informative to a weaker form, a linear form in finite elements that is a subset of the full vector space. All right. And in the next video, I'll talk about so this is magic, right? We did some magic, but there is some orthogonality and some error between however we're approximating it versus the real thing. And that will be the more mind-blowing thing that I'll go over next episode, okay? But hopefully this makes sense. All right, see you guys next time.